Thank you very much, Julia and Luca, for inviting me and giving me this great spot in the schedule. So I'm going to use it as kind of a commercial break to advertise some problems which I think are really important. And so the result is something from a few years ago, which we proved with Sergey Norin. It's a very general result about in extremal combinatorics, and there are some very general and I think very important open problems there, which I'm going to talk about later in the talk. So let me start by being a bit vague and just talk about what is the general approach here, or general area that we study. So extremal graph theory, we know it's a very old area. It dates to for more than a century ago, result of Mantel about densities of triangles. Density of a graph to be the edge density required to see a triangle in a graph. And there are many results since then and many different proofs and ideas, but we see some techniques are very common in this area, like Cauchy-Schwarz, as we have already seen in some of the previous talks, and say other things like induction. And there are new results or new way of looking at this whole area from a very general perspective, and these works of Friedman, Lovász-Schreiber, then subsequent works by Szegedy, Razborov, and other people, which kind of explain why we see, for example, why Cauchy-Schwarz is such a powerful tool in this area. And it turns out there is some rich algebraic structure between this underlying many of these techniques, and that's kind of explains these things. And as a consequence, we find neater proofs, like more soft proofs, as for example what Terry was talking in the previous talk. We can get rid of epsilons and lower order terms, and proofs look neater. And the actually more amazing thing is that we find some powerful techniques which kind of were overlooked previously to prove things in a semi-automatic way. And these were very successful in the past 3 or 4 years. So I'm going to mention a few amazing consequences of this. So in extremal graph theory, or extremal graph theory of dense graphs, basically, we are interested in the following quantity. So we count the number of copies of a graph H in G. Think of G as a huge graph and H as a small graph, and normalize it properly. We can think of these as moments of the graph G. So as in statistics, when you have a distribution, you'd look at the moments, or a random variable, look at the moments. Here we kind of think of these as kind of a statistics of the graph G. So we can look at these and try to understand global things about the graph G. So Nati Lineal gave a talk about these things and advertised them in the beginning of this semester here in Simons, and he was saying that this kind of can be thought of as some new branch of statistics, where we have these huge graphs, say, coming from biology or from social networks, and we want to treat them as distributions or something like that. Look at these samples. We can take samples and kind of estimate these densities, and by looking at them, say something about, like, make a guess for the big graph, as you do in statistics, saying that this looks like a normal distribution or Poisson distribution, things like that. So it's very important to understand the relations between these things. And if you look at the literature of extremal graph theory, you see that many of the results in this area can be interpreted or rewritten as basically inequalities between these subgraph densities for small graphs, such as Mantel's theorem, which I'm going to mention later. And there is a kind of an important theorem, which is one of the first theorems which initiated this way of looking at the area, is that says that every such inequality follows from the fact that some infinite matrix, which I'm going to formally define later, is positive semi-definite. So just this positive semi-definiteness fact implies all these inequalities. And you can interpret this as saying that all these inequalities follow from possibly infinitely many applications of Cauchy-Schwarz. So you apply all these Cauchy-Schwarzes, you add them up, and you get the inequality. So every inequality can be proved in this way. And Razborov, continuing this work, defined actually a formal calculus which included these Cauchy-Schwarzes and also some other things like induction, and kind of defined a more formal calculus for proving these inequalities. Okay, so I'll mention before giving you the formal definitions, I'll mention some of the incredible applications of this thing. So one is that now we have basically an automatic way of proving things, which was very successful. So it's basically you write your inequality as you feed it to a semi-definite program solver, and in many cases, it just gives you immediately a proof, basically, without even trying anything. So, for example, Razborov, this is one of the first applications. He just he found significant improvements over the best known bounds for Turan hypergraph problem, which some people consider one of the most important problems in extremal graph theory. And two of the other applications that just I was involved was the conjecture of Sidorenko and independently by Jager, Stovicek, and Thomason. And again, we didn't do really any any thinking here. Just we plugged the problem to the program and spit out the proof for us. And another thing was even a conjecture of Erdős about density of 5 cycles. Again, really no mathematical struggling. It's just a computer. But you can also involve them as add this extra power to your usual thinking power. So you can. This is a powerful machinery which can assist us. And a very important example is Razborov's proof that found the exact relation between minimal density of triangles, given exact formula for minimal density of triangles, knowing the edge density of a graph. And he proved Turan's hypergraph problem again under extra mild conditions. And these are from the beginning of this, from a few years ago. And recently, it's just, there's so many applications now that I can't really list all of them. But just, very recently I saw a paper again, another conjecture of Erdős solved with this, with very little effort. Most of the work was done again by computer. You can sometimes apply them to unexpected problems, really. They're not even about edge density of graphs. For example, in crossing number of complete bipartite graphs, Sergei Norin and Yuri, which they improved the bound significantly for this using this STP machinery. So when you look at these applications, the first question you ask is that, well, how far can you go? Maybe we can just prove everything using this machinery. Like maybe there's an algorithm which can prove everything. Maybe the only trouble is that computers are not powerful enough. That's why we can't prove some conjectures of Erdős, things like that. And so Razborov actually writes this. This is a direct quote from his paper on flag algebras. And he stated this as saying that he thinks this is the most important problem in extremal combinatorics. That is it true that every true algebraic inequality between subgraph densities can be proved using a finite amount of manipulations with subgraph densities of finitely many graphs? And then he actually states some, formalized some precise conjectures. And what we did is we prove undecidability result basically gives a very negative answer to these questions, all these questions, showing that no, this lack of computational power is not the obstacle. Actually, these problems are inherently difficult. So now I'll try to be more precise, give you the formal definitions. So extremal graph theory, as I mentioned earlier in the talk, it's about understanding the relation between densities of graphs. Instead of densities, I'm going to work with something similar called homomorphism densities, and these two are equivalent in some sense, up to just some little O error and some just normalizing factor depends. And let me define it. The homomorphism density of a graph H in a big graph G is the probability that a random map is edge preserving. So I'm going to map vertices of this small graph H uniformly and independently at random to vertices of G. And I'm interested in the probability that all the edges were mapped to edges. So this red arrows here correspond to a valid homomorphism. All the edges are mapped to edges there. I'm going to denote this by T sub H of G. And another way, so these maps are called homomorphisms, and this basically is the probability that a random map is a homomorphism. And asymptotically, as I mentioned earlier, these two are equivalent, so we can just pick whichever we want and work with that. And this T, like homomorphism density, is a bit more convenient because we don't require the map to be, for example, injective, and the automorphisms of the graph are irrelevant. And so we get nice identities. So for example, the following, which I'm going to use later, is that if you have two graphs, H1 and H2, and if you look at their disjoint union, I'm going to have the following identity, that the probability that a random map from the disjoint union is a homomorphism is just the product of the probability that the first mapping this part gives you a homomorphism times the probability that mapping this other graph gives you a homomorphism, right? Everything is independent. So I want all these edges to be mapped to edges and all these edges here mapped to edges. So I can just multiply that. So I get this nice identity. Okay, so we can state many classical results in this language. For example, Goodman's bound says that the density of triangles is lower bounded by the following: twice the density of edges squared minus the edge density. I'm going to use this result actually later. So it's a neat inequality between these densities. Another thing is that now any such algebraic inequality, I can actually convert it to a linear inequality using what I had in the previous slide. So here the problem is that I have a quadratic inequality. This is squared. But I know how to turn that into just power 1. I can write this as just T of K2 disjoint union K2, right? Two disjoint union of edges. So by what I had in the previous slide, these two are equal. So I get a linear inequality like that. So I can state Goodman's bound in the following way. Okay, so more notation. I'm going to work with something more general than graphs, and those are called partially labeled graphs. So what is a partially labeled graph? It's just a graph where some of the vertices are labeled with, say, natural numbers. So for example, this graph on 4 vertices is a partially labeled graph. This one is labeled with 2, this one is labeled with 3, and these two ones are not labeled. Okay, and now I want to generalize this homomorphism density to partially labeled graphs. So recall that this was the probability that a random map is a homomorphism. Now, so when I have a partially labeled graph, I also will require to have a map from the set of labels to G, which will tell me where do labeled vertices will go. So phi tells me where each label should be mapped, and then I'll define this probability given phi to be the probability that I'm going to get a homomorphism if I respect phi. So if my map is an extension of phi, f restricted to L is phi. So think of these labeled vertices as you pin them on the graph, and then you map everything else randomly, and you want to get a homomorphism.
Do the labels attached to specific nodes? Or?
Yes, so some nodes are labeled in the graph H, and this map phi tells you where those should go, and then after that you do the probabilistic step. So here I have this one labeled graph. Phi tells me that this vertex should go here, and now the T is defined as will be 3 over 4. So the only way to get a homomorphism is to map this other unlabeled vertex to one of these 3 vertices. So 3 over out of the 6 choices I have, so I get half. Kind of gives me normalized degree of this vertex, for example. So another notation is this bracket operator will just erase the label. So if I have a labeled graph, if I write it in this bracket, it means that I'm erasing the labels. So it will convert this labeled vertex to an unlabeled vertex here. And it has a meaning, analytic meaning. I can think of this as taking a random phi, right? So if I average all these maps, all these densities with fixed phis over a choice of random phi, I'm going to get just a probability that a random map is a homomorphism. So I'll get this identity. Just erasing labels means averaging over random phis. Okay. So recall that I had this identity here. And motivated by this identity, I can define the product of 2 graphs to be just a disjoint union. So I just basically convert this to a definition. I'm defining the product of 2 graphs to be their disjoint union. Now I want to define similarly the products of partial labeled graphs. let me give you first a definition and then say what identity it corresponds to. So what I'll do is I'll take their disjoint union as I do for unlabeled graphs, but then I'll identify vertices with the same labels. Okay, and then, but this might lead to multiple edges, and in that case, I'll just keep one of them. So for example, take these two partial labeled graphs. I want to multiply them. I'm identifying 1 with 1, 2 with 2, 3 with 3. And because of that, I'm going to see, for example, a multiple edge between 1 and 2. It exists in both, but I'm going to just keep one of them. 1 is adjacent to 3 here. I'll have that edge. 3 is adjacent to 2. I'll have that edge. So on. So I'll keep all the edges between labeled graphs in both graphs. And then the unlabeled vertices will be just remain disjoint. So this part will remain here as kind of a tangled part, and this other one here. Right? So it's just gluing the two graphs over the labeled vertices according to the labels. Now, why is this a good definition? Suppose I have two graphs with labels L1 and L2, and I have a map which tells me where do labels should go. So phi maps all the labels in L1 union L2 to G. Now I claim that I have the following identity. If I multiply these two things, homomorphism density of H1 and H2, then I'll get the homomorphism density of H1 times H2. So let's see why that's true. So I have these two labeled graphs. Phi tells me where do labeled vertices should go. So note that in both sides, to get a homomorphism, I need to map all the edges between red vertices correctly, right, to edges. Otherwise, I'm going to get 0 in both sides. So if phi maps any edge here, say 3 to edge between 3 and 2 to a non-edge, I'm going to get 0 here and I'm going to get 0 here, because both of them are mapping these labeled vertices the same way, and I'm keeping all the adjacencies between red vertices. And the other thing, now once you condition on that, these two events become independent. The other vertices are being mapped independently, right? So take so condition on these green arrows, then take any map that maps this part randomly and this part randomly. I can just combine those two maps and get a map which maps all these two vertices randomly. And again, it's just in both sides, I'm just looking at the probability that all these adjacencies between between blue vertices and also between blue and red vertices are mapped correctly. It's a very simple observation, but so it says, kind of shows that this definition that we had is a good definition for a product. So as I said, well, the whole thing we are looking at are these linear inequalities between homomorphism densities, and we want to see when are they valid for all graphs G. For example, Goodman's bound, we saw that before. That's something which is valid for all graphs. Okay, so let's see how we can prove such an inequality. I'm going to give you a way of proving those. Consider a set of partially labeled graphs with labels coming from a set L, and pick some coefficients. So these are just real numbers. They can be negative, positive. And the map phi, which tells me where labels go to this graph G. Now, let's do the following. Let's look at the sum of bi, t, hi, phi of G. So this can be a negative number, a positive number. I'm going to square it to make sure that it's a positive number. So this is at least 0. Now we can expand this. So what will be the expansion? I'll get this double sum, bi, bj, t, hi, phi, t, j, phi. But now I know what this is by my definition, right? So this is nothing but t of hi times phi hj, the way I defined before, this gluing operator, and phi of G. So I know that this inequality holds, right? So for any graph G and any given phi, this is always positive with these partial labeled graphs. So this is not exactly what we wanted. Excuse me. The reason is I have this phi. But how do I get rid of phi? I've already mentioned this before, right? So you can just average now over all random phis. So this is what we proved in the previous step. And now if I average over phi, take the expected value over phi, well, it's still going to be positive because this is positive for all phi. So this will just means that removing the labels. So this is a way of proving such inequalities. Any bi, bj, any set of partially labeled graphs, I have this identity. This is always positive.
Does you're averaging over all phi a fixed number of labels, or doesn't it matter?
Yeah, I mean labels are coming from the set L. I mean I have a finite set of finite graphs.
Okay.
Right. Okay.
Yeah.
Okay, so I know that I can prove such inequalities. So these are always positive. Okay, so let me say. So suppose I have these partially labeled graphs. Now I know the following facts. So for every graph G, first of all, tk1 of G is always 1. Right? That's always the case. Another trivial identity is that if I take the union of H and K1, disjoint union, this is going to be just TH of G times TK1 of G, which is the same as TK of H because of the first condition. And the third condition is that this infinite matrix, whose ijth entry is this, is positive semi-definite. This is the definition of positive semi-definiteness for this matrix, right? Whose entries are these. So for every graph G, I have this positive semi-definite matrix. And it turns out this result of Friedman, Loess, and Shriver that I mentioned earlier is that these three conditions suffice to characterize the relation between all these subgraph densities. So if I have a map T which satisfies these three conditions, it means that it's a density of these graphs in some graph G. Right? So given such a map, I can construct a G. In the limit, actually. It's not exactly G, but it's a limit of this, like a graph on what Terry talked before. But in other words, if we could optimize over this semi-definite, positive semi-definiteness of this infinite matrix, we could solve all those linear inequality. Okay. So the next notation I'm going to define is just going to, it's a very abstract thing, and it just simplifies writing things. So it's not, I mean, it's basically an abstract nonsense. So a quantum graph is just a formal linear combination of graphs. So given any set of graphs, h1 to hk, and some numbers, I'll define this formal linear combination as, call it quantum graph. There's no semantics here, right? It's just a definition of it. Now, we call it positive if for every graph G, the following identity holds. So our goal is to understand what is this set of positive quantum graphs. For example, Goodman bounds corresponds to the fact that this quantum graph is positive. Okay, we can do the same thing with partially labeled quantum graphs. I can look at their formal linear combinations and call them partially labeled quantum graphs. Now, I know how to multiply two partially labeled quantum graphs. I can extend it to this partially labeled quantum graphs to turn it into an algebra. So given these two linear combinations, formal linear combinations, the product is defined the following way. So you just expand it and then take pairwise products, which is we know how to do, just glue them over the labels, right? So this turns this whole partially labeled quantum graphs into an algebra. And I have this linear operator which was erasing the labels. It's a linear operator from this algebra to this other algebra. And for example, what we did in a few slides ago, squaring and then unlabeling corresponds to this identity here. So you can square it, expand it, you get this, and then this is a linear operator, so you can just take it in and get these identities. So what this said before, what this says is that given any labeled quantum graph, the following is positive. We saw that before. Now, this was one way of constructing positive quantum graphs. I can also add them up. If I have a bunch of quantum graphs, I can just add them and get another positive quantum graph. So given partially labeled quantum graphs G1 to GK, if I square them and add them up and then unlabeled, I'm going to get another valid inequality. And this question, due to Loess and Szegedy, and in a slightly different form to Razborov, asks whether, is it true that any valid inequalities, or in other words, any positive quantum graph, can be expressed as the sum of finite number of squares, sums of squares of this finite number of quantum graphs. And it was quite a coincidence, apparently. This is listed in Lovaas's list of open problems, problem 17. It's really related to Hilbert's 17th problem. And according to Latzi, this was a coincidence, so it wasn't intentional. Okay, so... no, unfortunately not, but what we saw was kind of a 10th problem in the end. Yeah. I don't know if it can be changed. We ask him to. So Lovaas and Szegedi and independently Razborov observed that the following is true. If we are only interested in approximation, we can do this. If f is positive, then we can approximate it with the sums of a square. For any epsilon, you find a k and this nice expression that the difference is epsilon. So this basically says if you're caring about bounds, not exact solutions, a computer should really beat humans in this, and it does, as you see in application. You plug it, you get a huge improvement what people were trying to do before, over what people were trying to do before. For any epsilon, positive number epsilon. You can think of it as epsilon times k1. Okay. Yeah, k1 is kind of the identity of the algebra. So, and what we show is that the answer to this question is negative. Actually, something even stronger that I'm going to mention later. So what we first did was we constructed a counterexample to this, but then we found stronger results. So because I'm going to talk about the stronger results, I'll just mention this where this construction comes from without really giving you the proof. So you talk about positivity and sums of squares. So where should one look at? Of course, polynomials, right? And for polynomials, again, we know sums of squares is always positive, and Hilbert first observed that a long time ago that there are three variable positive homogeneous polynomials which are not sums of squares of polynomials. So this question, setting of polynomials, has a counterexample. One simple one is Motzkin's polynomial over three variables, degree 6. It's positive. You can write it as sums of squares of polynomials. And what we did was just we turned this into something about quantum. So we took that and converted it to a quantum graph, which writing it as sums of squares of quantum graphs would imply that this is also sums of squares of polynomials. So that Hilbert's 17th or Latzi's 17th problem was falsified by this. No, they're not that big, so they're on tens vertices or something. Okay, so, well, for polynomials, you can write them as sums of squares of polynomials, but we know that we can write any positive polynomial as sums of squares of rational functions. So just polynomials divided by polynomial squares. So this is a result of Artin from 27, which was an answer solution to Hilbert's 17th problem. And actually, again, Latzi in his collection of open problems kind of expected that the answer to the other one would be negative, and he also asked this, maybe some analog of Artin's theorem would be true. But note that this has an interesting consequence, and that is that checking the positivity of a polynomial is a decidable problem. You can do it by a computer, and the reason is we do the following two things in parallel. First of all, we check the value of the polynomial over rational numbers, trying to negate it, to make it negative, trying to find some setting of rational numbers which makes the polynomial negative. And in parallel, we can also try to write it as sums of squares. So actually, in this theorem, you can assume that coefficients are rational. So I have these two countable sets. I just go over all the possible choices in parallel. Either at some point I'll find some assignment to variables which makes the polynomial negative, or I'll succeed in writing it as sums of squares. So in any case, I'll know the answer, whether it's positive or not at some point. So this is decidable. And if the analog of Artin's theorem would be true for quantum graphs, we'll also get decidability there for verifying the validity of those inequalities. Okay. Again, so I mentioned these things in previous slide. So we know with knowing this would imply decidability, and actually, amazingly, no one asked this before. Neither Lovász and Szegedi nor Razborov. But this is really the natural question to ask, and it's stronger than all of those previous ones. And what we showed is that this is undecidable. So given these coefficients and graphs, there's no algorithm which will tell you whether this inequality holds. So I'll mention the main part of the proof. It's not really very difficult. It's a very short proof. And it's now actually in Lovász's book on this topic. So this is what I want to show. Given these coefficients and graphs, is it true that this inequality holds for every graph G? Equivalently, I can work with polynomials. So linear and polynomial are the same because of this trick we had with replacing graphs with disjoint unions. So it's equivalent to saying that given a polynomial and these graphs, is it true that if I assign these densities to variables of the polynomial, it's always non-negative? Right? Okay, so this is the new statement, which was equivalent to what we wanted to do. And I'm not going to give you exactly the proof of this, but I'm going to prove something very similar, which hopefully will convince you that, give you the idea why this is undecidable. So here, note that all these densities are coming from one graph G. In this new problem, I'm going to be a bit looser, and the condition is a bit stronger that I'm allowed to use densities of various graphs, G1 to Gk. So I have a polynomial P over these 2k variables. And the question is, if I substitute the edge density as triangle densities of these k graphs, is it true that this is always non-negative? On the other hand, it's very simple, right? I'm just working with edge and triangle, not even any fancy graphs. This thing, densities of edges and triangles. But k different graphs. Okay, so the proof of this is not so difficult. So I'm going to use two basic ingredients. Maybe the whole meat is here in Matyashevich's solution to Hilbert's 10th problem. So he showed that this deciding whether a polynomial is non-negative over sets of integers, so you're only allowed to assign integer values to variables, that's undecidable. You can't do that using computer. And you can just do a simple trick and convert it to the following. Instead of integers, I'm going to look at this other countable set, other discrete set. So I'm interested whether I can make this polynomial negative over the set of numbers of the form 1 minus 1 over n. This you can, I'm sure all of you believe that this is undecidable, knowing Matyashevich's theorem. Okay, so this is the main ingredient. The other ingredient is this result of new result of Razborov. Actually, Bolobash's older result would also suffice. Let me say what this means, what these results say. So this picture here, what I have here, completely describes the relation between edge density and triangle density in a graph G. So x-axis here corresponds to edge density, y-axis corresponds to triangle density. And this gray area is all the densities, possible densities that can be achieved using graphs or graph limits. So it's a closure of everything I can get with graphs. So any point here, I can find a graph limit whose edge density is the x coordinate and whose triangle density is the y coordinate. And Goodman's bound, which we saw before, says that this triangle density is above this Goodman's bound. So this curve at the bottom was Goodman's result. And the result of Bolobash, an old result of Bolobash, says that this Goodman bound is sharp only on points of the following form, 1 minus 1 over n. So these are balanced two-run graphs, which show that this Goodman's bound is sharp. And actually, the new result of Razborov is that it completely describes this gray area, which says that describes the actual lower bound. So there's infinitely many curves here separated. So you see here, there is a way of using edge density and triangle density to get this discrete case, right? Discrete set. That's the main idea of proving the undecidability. Okay, so I'll give you the reduction. Let S denote this gray area, and let G denote the Goodman's bound. So it's this curve here at the lower part of this gray area. 2x squared minus x, which corresponds to Goodman's bound. Okay, so now I have a polynomial p as an input. I want to do a reduction, so I'll use this to construct the following polynomial q. So q is, I multiply p by this positive polynomial, and I took this high enough power to make it to kind of dump it down to make it a small number, 1 minus xi to the 6. And then here on this second term, I have a large integer c, which depends on p. You can take the sums of coefficients of p, for example, here, or 10 times that, some large number, just depending on p, times the following. So yi minus g of xi. Now, so this is my reduction. I'm claiming that the followings are equivalent. One is that this thing, that p is negative, can be made negative by some assignment of these kind of numbers to variables. And we know checking this is undecidable because of Matiashevich's result. And the equivalent thing is that this new polynomial q is negative for some values of xi and yi which come from gray area. So all these things are only allowed to be picked from the gray area. So let's see why that is true. First of all, suppose, so let me first show this implication from top to bottom. Suppose p is negative for this assignment. I can take these yi's to be equal to gxi. That's in the gray area for these kind of points, right? So these are where Goodman's bound matches the gray area, touches the gray area. So this part becomes negative, p is negative, and I'm multiplying some positive number, so q will be made negative. So this direction. The right, this is 0, but this one is positive, right? Negative, sorry. So I'm going to get a negative value for q. Now the other part is the trickier part, but again, not so difficult. So now suppose q is negative for some assignment coming from gray area. Why does that mean that p is negative for one of these points? The thing is, if these xi's are not of this form, then I know there's a separation between this gray area and this Goodman's bound. So there is a significant difference here between yi and gxi. yi is strictly greater than gxi. And I'm multiplying that to a big number here, cp. And I'm making p smaller by multiplying it to this. So basically, the derivative go in the right direction, and this term will be more negative than this can be positive. So it will make this whole thing... so what did I want to say? This is more positive, yeah, than this can be more negative. Exactly. So p has to be negative in that case too, one of those points. Okay, so that's really just a simple reduction. And gray area, we know that just corresponds to what we get from edge density and triangle density. So this last equivalence is really, trivial. Not trivial, really follows from Rasborov's result. Okay, so that's the proof of that undecidability that I had before. So this leaves us, so where do we go from here? So this thing is undecidable. Is there a nice general way of approaching these inequalities? So one thing now we can do is, well, maybe we can hope decidability for some restricted classes of graphs. And actually, an old result of Bolobash implies that if you have such a linear inequality involving only cliques, this is decidable. So, and basically Bolobash's result says that this is always minimized when you look at these densities inside the cliques, and then you can optimize over that. So this is decidable. Maybe the next class one wants to look at are polynomials involving clique densities, which corresponds to linear inequalities involving unions of cliques, right? Polynomials means just taking disjoint unions. So instead of cliques, I'm allowed to put the unions of, say, triangle, edge, and so on. Is that decidable? Probably no, but I don't know any way of proving it. Another really important thing is to understand this monstrous object, which is, so for every graph G, as I said, these things correspond to we can think of them as as the moments of this graph. So for every graph G, we get a list of numbers, which is, you can think of it as the statistics of G, or it's the profile of the G. And this is a point in the set 0, 1 to the n. And if you look at all graphs G, we get this huge set of points in 0, 1 to the n, and we can take its closure. Let's call this R. So this is really a monstrous set. We know very, very little about this. For example, it's not even so easy to prove that it has non-empty interior. So that's an old result of Erdős, Lovász, and Spencer from, I think, late 60s or early 70s, I don't remember. So they showed that it has a positive non-empty interior. And what does Razborov's result, for example, say? It just describes the projection of this R to two coordinates, triangles and edges. And so even understanding the projection of R to two coordinates was a very difficult task. So, I mean, it seems describing the whole set R is impossible, but we can try to understand more things about it. Okay, so another way of approaching these inequalities from general perspective is through graph limits. So this is going to be my last slide. So as Terry mentioned in his talk, if you have a convergent sequence of graphs, you can represent the limit as this nice object, symmetric measurable function from 0, 1 squared to 0, 1. Now, you can talk about now finitely forcible graph ones. What are these? So these are points in R which are uniquely determined by a finite number of coordinates. Suppose I have this long list of numbers, profile of a graph, and I tell you a few coordinates, say edge density and density of 4 cycle. That might determine the whole sequence. For example, we know that's the case for limits of random graphs. If I know the edge density of a graph limit is half and the 4 cycle density is 1 over 16, then I know this corresponds to the W, which is just the constant half function, which is the limits of random graphs, for example. So that's finitely forcible. So there was or still maybe there's a general hope. So there are two related conjectures. First is by Lazzi, which says that if I have an inequality which is not valid, or you can think of it in the other direction, feasible inequality, this sum is at most 0. So there is some W which makes this negative. Then there is also some finitely forcible W. It's a really beautiful conjecture, but we have no idea how to approach it. I talked to Balaj and Lazzi. It's just, there's really even no partial result. Another equivalent way of saying it is that, suppose I give you some densities, say density of edge, density of triangle, density of 4 cycle, and so on, and we know that there are some graph limits satisfy these densities. Can I fix more densities to get a finitely forcible graph? It might be possible, it might not. So one conjecture is this. The second conjecture, which kind of not doing so well these days, is that finitely forcible graph ones have simple structures. So initially people thought that they're just basically step functions in the following sense, that they are just, you take this 0, 1 square and you partition it to some parts like this, and then they're constant in different parts, 0, 1 say here, 0, half here, so on. So this was the initial conjecture, which very soon refuted by constructing a finitely forcible graphon, which was of this form, 1 here, 0 here. And then this finite dimensional conjecture was kind of the last conjecture, precise conjecture, which was saying that, well, I'll say what it says exactly by mentioning this new announced result, which is still the paper, I haven't seen the paper, by Glebov, Klimoshova, and Dan Kroll, which say that there are finitely forcible W's such that the following holds. Let's look at the rows of W's. So for every value of x, let's look at this function Wx and is a function of the second coordinate, right? So you get this set of functions. And let's endow this space with L1 distance. Right, W is like a matrix, but over 0, 1. Rows are indexed by interval 0, 1. So look at the rows with L1 distance. This might contain a subset. So they constructed a finite forcible W such that this contains a subset which is homeomorphic to 0, 1 to infinity. So it's really very infinite dimensional, this row set. So the original conjecture was that if you do this with L1 distance, this is always be a finite dimension. Actually, what Lovász and Szegedy had was that they only knew constructions of one-dimensional objects, but they kind of suspected that finite might be possible and not infinite is not possible. Then Sergei Norin, which was my co-author in this work, he constructed d-dimensional finitely forcible graphons for every d, and then these people extended those ideas and actually managed to construct infinite dimension. So in this, I mean, this conjecture is kind of refuted. I don't know if there is any other simple structure one might expect. The only positive result one knows is that, again, due to Lovász and Szegedy, is that the set of finitely forcible graphons is a first category set. So it's a countable union of nowhere dense sets. So it's very, very sparse compared to set of all graphons, but no really explicit structures now. So I'll stop here.
Questions?
Yes.
If I give you some parameters like S density, triangle density, can we sample such graphs at random?
Random. I know there are some works about that, but I'm not sure about the general theorem. Yes, I don't know. Say.
But we don't even know if there exists such a graph. Yeah, part of the question.
Oh, pardon.
I mean, let's say you take from the gray area and how to, the model.
Yes.
So Boloba's result was that this inequalities in cliques is decidable, but do we know what's decidable in polynomial time, or is there any conjecture?
I don't know if it's polynomial. So the decidability comes from the fact that you only need to look at cliques for that. It's an optimization of that. Probably it's polynomial. Yeah.
But the question was, so let's say this is polynomial, like, do either any reasonable conjecture on what might be decidable in polynomial time?
No, I don't know. Yeah, actually, that one thing about this area is that for some reason computer scientists haven't been working on this area that much as I think they should. It's mostly really pure mathematicians and combinatorics. It's really, I mean, it's very computer science area, right? So you apply these techniques, you can actually find proofs using them, and then there are questions about exactly how efficient you can be for certain problems and so on. I think it should be more advertised. Yes.
So maybe it's the case that inequalities between 3 graphs or 4 graphs can be.
Yeah, maybe. So what we have is, I think, between 9 graphs, 10 graphs, something like that.
And
But
algebraic inequalities.
yes, yeah, not linear.
Yeah.
This corresponds to being able to deal with elliptic curves, but not the regular polynomials with 9 variables.
Let's thank Hamad again.
Thank you.